You went through an activity yesterday. How did that go? You submitted everything, because anything that's not submitted when I check grade it for period, it's not in that box or it's not online, then it's a 0. Because I told you this last time. If you're in class, I expect you to be working, and the only evidence I have that you're working in class is if that work is turned in. No extended time, no special circumstances. If it got halfway done, it's halfway done. If it's a quarter of the way done, it's a quarter of the way done. Whatever it is, I will make a judgment, give you a grade, but a 0 is what you're going to get if you wait too long, because it's supposed to be done and turned in at the end of the period when I'm absent. And I have numerous other doctor's appointments and other activities I have to do during the year. So I expect to be absent 5 or 6 more times for the rest of the year.
Like this 2020?
The whole school year. 5 or 6 more times during the school year. When I'm absent, I don't want this to be a thing. When I'm absent, you turn in the work. I haven't talked to Mr. Tolles. You had Mr. Tolles yesterday. I haven't spoken to him, but when I do, the quiz, which will be tomorrow, will be either open notes or not, depending on how well you worked. Does that make sense? Okay. You read that, my message? Did you? Did you read the Jupiter message? All right. Okay. So, tell me about your project. What did you do? Say that again? Melting point. Okay, what about melting point? What's so interesting about melting point? By the way, that lady that you read about that discovered agar with her husband, her and her husband were millionaires. After that, she discovered a way to keep the gel stable. Agar was used in cooking before it was used in science. Cooking, in fact, is chemistry. Being a good chef is being a good chemist. A specialized version, surely. All right, so tell me, what did you learn? Well, you knew what melting point was. What was so important about melting point? How can what? How can it affect someone's health? How did they do that? How did it affect someone's health? It had something to do with tuberculosis, you're right.
We found out the symptoms and what happens when you do have tuberculosis.
All right. You know it's a bacteria?
Yeah.
All right. You know that they had to have a way to grow the bacteria so they can test it and keep it alive, right? And they couldn't keep the agar solid in the incubator because it would melt, or the gel solid in the incubator because it would melt. So they added agar, which is a seaweed protein. And all of a sudden, the gel held even in an incubator. And they had to keep it in an incubator because bacteria grows in warm temperatures. So if you didn't, who was absent yesterday? Anybody? Okay, so everybody was here yesterday, so I expect to see 100% of the work turned in. Now let's go on and start talking about some of the rest of the ideas that we have to talk about. Have we talked about atoms at all? So let's review. Let's go back. I'd like to start, especially when I'm absent, start where we left off. And we did talk about melting point, right?
Are we going to be using that chart today?
What chart? No, that's not for you. Melting point, we talked about freezing point. What do we know about melting point and freezing point? What do you know? Quick review for tomorrow's quiz. Sounds like people have to review. I'm not going to go over it all again, but they're the same temperature. The temperature at which things melt and freeze is specific for a substance. So the only difference is it cooling? Is it losing heat? Or is it gaining heat? I hope you know if it's losing heat, it's cooling. Correct? If it's losing heat, it's cooling. If it's gaining heat, it is warming. So that's the only difference. And same thing goes for, by the way, evaporation point and condensation point. Same temperature for any specific substance. The only difference is it warming up or is it cooling down? Is it losing heat or is it gaining heat? And yes, things do freeze at 1,000 degrees Fahrenheit. And things do freeze at negative something Fahrenheit. It all depends on the substance. It depends on the conditions. So to remind you, the other things we talked about is that you have gases where the particles, and I'm going to call them particles right now because we're going to call them molecules and atoms in a little bit. But when the particles are far apart, we call them a gas. When they're closer together, they're attracting each other, they're closer together, trying to make the same number of particles in each. And then the last one's when they're closest together. So liquid and gas. I'm sorry, liquid, solid. Thank you. So interestingly, liquid and gas are called fluids. That's because they flow. They flow. Solids don't really flow that easily. They can flow. With enough energy, they can flow. But both liquids and gases are fluids. So I'm going to make something I'm sure you've seen before, a Venn diagram. I'm going to make gases the yellow circle, the liquids are going to be the blue circle, and the solids are going to be the red circle. The Olympics. Oh, I can't stand making a bad circle. All right. So some of these they share. So if the liquid, if this is liquid, this is gas, and this is solids. Gases and liquids, they flow. Each individual one flows. Gases fill up the space. They fill up the space. they take up. So gases fill up the space they're in. But the point is that sometimes solids can act like liquids given the right conditions. And they don't act like gases, though. Gases are extremely far apart, remember. Gases are very far apart. So let's review, because I think I stopped recording. So gases are they do flow, they fill up the space they're in, they're compressible, very much like a spray can. What is a spray can? Compressed air. You release it. Obviously, they put stuff in it. They put some liquid in it, like hairspray. We'll have hairspray gel in it, or whatever. And the compressed gas in, when you open the valve, the gas comes shooting out. When a liquid does flow, obviously, you can pour liquid. By the way, did you know you can pour gas, too? You can take carbon dioxide gas. You've heard of dry ice? You have a dry ice machine, then you've seen the smoke flow. It literally flows. And it's up here, if I had a dry ice machine up here, you would see it flow right up and flow down. You could literally take a cup of that gas and pour it. Okay? So it's pourable. It's because it flows. It takes up the shape of the container. Liquids take up the shape of the container. So do gases, but gases fill up the entire space. Liquids don't. You know that. You can have a glass that's half empty. You can't have that with a gas. If there's a container, it's going to fill up the container. Liquids are not compressible. Have you ever seen a machine that can lift a couple 100 pounds, a forklift, or a crane? Except for those that use pulley systems, a lot of them use hydraulic systems. What they are liquids that can't be compressed, are squeezed, or pushed in one direction or another. That increases the force and allows you to move really heavy things. So the fact that liquids are not compressible are very important. They lead to hydraulic systems. So these are the three basic states of matter, and you're very familiar with solids, so I don't have to go into their properties. Some other properties you should be thinking about, though, is sound waves travel sound. When we're thinking about biology, sound are what we call compression waves. Light is energy, but sound is a series of pushes. You push. So you push out with your breath. You send a wave of air. Like when you hit a ripple, when you push water, what happens to water? It has waves. Well, you're going to do the same thing. You do the same thing with air, except when these waves are waves of air, of gas. And when you push them, they create these waves in the gas. That's why there's no sound in space. Why is there no sound in space? There's no air. There's nothing to conduct the gas. You need material to conduct the wave. The closer the material, the better. So I'm going to give you an example. If I have one atom or molecule here and another one over here, for instance, let's think of this as air, and then this, in order for a wave to continue, and you've all done this, have you ever been to a sports event where they did the human wave? Where everybody stands up and then sits down, stands up and sits down, so it's like have you seen that at least? Yeah. So that's just this atom or molecule traveling and hitting this atom or molecule. And that continues. And so the closer these are, I hope you know, that's a gas and this is a liquid. Where's the sound going to be conducted faster? In the solid or liquid? if the time it takes to hit this 1 to hit 2, which is going to be the fastest to conduct sound? Solid is correct. So if this were gas and this were liquid and this were solid, then the time it takes for one particle to hit the next is going to be fastest in the solid and slowest in the gas. And that's what happens. Now, why can we hear better in gas than we can underwater or in solids? Because our ears are designed to pick up sound waves, which means gas waves. But have you ever seen in movies people put their ear to the ground? In fact, there's an old saying, put your ear to the ground. Native Americans would do that to listen. They would, but in old movies, I'm sure people did it all over the world. You put your ear to the ground because you can hear things moving miles away. But you have to be calm. You can't have any stomping around you. But if you're calm and you're listening, you can hear, for instance, big things like buffalo herds or horses. Like you can imagine if you were an enemy, you're being hunted by the cavalry. You put your ear to the ground, you can hear the cavalry running towards in some direction. Why? Because solid conduct sound better. Why do solids conduct sound better? Because the molecules are closer together. And in fact, this is what allows us to detect earthquakes. We listen for sounds, for vibrations in the earth, and those are earthquakes. So in any case, this wavelength, a wavelength is measured from here to here. A wavelength is measured from here to here. And so let me ask you a question. So they're all the same. So if they're the same sound, the length it takes that they travel depends on the energy they're moving, right? How close these waves are. How many times is this hit 1, hit 2, then hit 1, hit 2, then 1, hit 2? How many times is called frequency. Frequency is how many, whatever, per hertz. How many times something happens, I'm sorry, that's not per second. Hertz is per second. And hertz is the unit. Hertz is a measurement of how many times something happens every second. So have you ever tuned into a radio station? If you tuned into a radio station, you're tuning into a specific frequency. You're getting your machine to listen for a specific frequency. High frequencies sound like this. And low frequencies sound like this. So when you have high frequencies, a lot of them coming at your ear at a given moment, the waves are real close together. When the waves are low, I can't do much lower than this, I'm sure someone else can, but they're further apart. Low frequency, high frequency. Low frequency waves have to be shorter. Do you see that? Can you see why they have to be shorter? Because if the time measured is every second, waves per second, the second's not going to change. So to shove this many more waves past a point in a certain number of seconds, these waves have to be shorter. Does that make sense? Yes or no? The speed of the waves is constant. The speed of sound is the speed of sound. The The speed of light is the speed of light. Speed of sound is constant in a specific density and temperature. So it travels faster in solid than it does in liquid, but once if you're listening to it in a specific solid, the speed of it is going to be consistent. The only difference is how short the waves are. Are we clear with this? Because that's called wavelength. Again, lambda, which is a Greek letter, equals wavelength. The shorter the wavelength, the higher the energy. So high energy sounds, high frequency sounds are high energy, low frequency sounds are low energy. And low frequency so that's kind of a quick and dirty summary of physical science, something you should have been introduced to in middle school. Hopefully you were. If not, you've just been introduced to it here. So these compression waves that they got high and low frequencies. Well, it turns out that light has some similarities to sound. There are some major differences though. Light is not a compression wave. It is a wave, though. It does have a wave, which means it has what? If it has a wave, what does it have, considering what I just talked about? It has energy. Excellent. What else does it have? High and low. High and low what? Frequency. Excellent. Excellent. And wavelengths, right? Long and short wavelengths. So we have wavelengths that are high, which means they're close together, right? And I'm just scribbling here, I apologize. And then you have low frequency wavelengths. So wavelengths are longer, so they're lower frequency. I should draw that in black. All right. Man, I wish it was not so crooked. Sorry, sometimes I get a little OCD about things lining up, but whatever. So non-compression waves, they are energy. Their light is an energy. So there's no mass, no thing to hit. So it can travel through space, thank goodness, because that's how we get our energy on planet Earth is from the sun, and it's traveling through space. The light speed of sound is constant. Speed of light is constant. In any specific material. All right, so the speed of light is constant. But the frequencies can be different. So with sound, the frequency determines the note. You know the note, right? High note or low note, correct? Yes, you've heard singing, you listen to music. So the high notes and low notes are determined by the frequency and the wavelength. In light, the frequency, how often the every second a wave comes by determines the color. All right, so frequency and wavelength determine the color, or the part of the spectrum. In visible light, it's color, but not all frequency, not all light has color. Not all light, you can't see all light. In fact, we can only see a very small portion of all the light spectrum, of all the possible frequencies and wavelengths. We only see a very small portion of that frequency, of that spectrum. We only see red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. We only see the rainbow. Outside that, we don't see anything. You've heard of black lights? That is called ultraviolet, meaning it's beyond violet. UV, you've heard of UV light, ultraviolet. That means it's beyond, it's just light, but it's such a high frequency that we can't see it. We can't see it. Our eyes are not designed to see this kind of light. It does interact with things around us, and if you have a chemical that can absorb it and then release visible light, then you can see it. That's how black lights work. The reason they call them black lights is you cannot see the light, but you can see the paint and dyes that absorb that light and release it. So then have you heard of infrared? No, you've not heard of infrared? You know this is as heat. You've seen those in video games, the infrared goggles. Yes? They can see heat. Heat is infrared. When you see heat, when you feel heat, what you're feeling is this part of the light spectrum. It's below red. Below red. We normally can't see it. X-rays, radio waves, I should say first. Radio waves are over here. AM and FM, they're over here. Microwaves are over here. That's the symbol for micro. And X-rays are over here as well. They're high energy short waves. These are lower energy, long waves. Long waves, short waves. All right? And so that's the very quick one-day summary of physical science that you're going to need to understand photosynthesis and cellular respiration.